Good day, everyone. So, in today's lesson, we'll be looking at volume density and relative density for fluid at rest. So, these are the basic concepts and terminologies we use for fluid at rest. So, we'll be able to know the volume of fluid at rest, the density, as well as the relative density, and the law that governs this concept. So, let's dive into this. Okay, we know that when we talk about volume simply is the amount of space occupied by an object or substance, and it is measured in meter cube. Okay, so when an object occupies the space, okay, we know that that's the volume of that object, right? And depending on the type of space it's occupying, in terms of liquid, if you put that liquid inside a cube, then definitely the volume will be length times length times length, as you can see here. So this, for example, now, if we have content inside this cube here, to get the volume of this cube, it will be the length times the width, which is the same thing, and the height. Cube, all the sides are equal. To get the volume, it will be this length and this width, which is the same length, then times the height, which happen to be the same length. So L times L times L will give us meter cube. So a cube with side of 2 meters, now the volume will be 2 times 2 times 2, because each side is the same, 2, 2, 2. Right? That's what volume is, the amount of space, and by formula it is length times length times length. Density, on the other hand, is mass per unit volume. Okay, the mass of the substance per volume it occupies. Okay, so by symbol, we use the symbol to represent density, and the formula is density equal to m over v, where the m is the mass and the v is the volume. The unit of density is kilogram per meter cube. So sometimes it can be written in another way. So this kilogram per meter cube can also be expressed as kilogram per m with power minus 3. Okay, what just happened is that this slash, it turns to become power of minus. That's all. Okay, so either of them is the same thing. So density is the mass of the object, okay, occupied in the unit volume. Okay, and then we have what we call relative density. It's not the same thing as density, but they are related. When we say relative density, which we call it specific gravity. It is the ratio of a substance density to that of water. So when you find the ratio of one density to that of density of water, then you have found the relative density of that substance. Okay, so it is the ratio of the density of the substance to that of water density. So by formula, we can say that relative density, which most time we use RD to represent, we can say it means by formula is RD equals to density of, if it is let's say if it is kerosene, so the density of kerosene over density of water. Okay, of water. Now this formula, now this relative density now is for what? For kerosene. Relative density of kerosene will now be density of kerosene over density of water. Sometimes it could also be mass of kerosene over mass of equal volume of water. Okay, so either you say density or you use mass, but it will be the same. If you mention density as numerator, it will be the same for numerator. But the quantity up is the one that owns the relative density. And because it is the same quantity, so it is unitless. Density unit and density unit. So the unit of relative density is what is it does not exist. So we can say that it is dimensionless. So when a quantity does not have a unit, we say it is what? Dimensionless. Okay, now this relative density helps us to know when an object can float and when an object can sink. If this is a container now, and then this container has liquid inside, let's say the liquid is water. Okay, now if you put an object, maybe let's say you put a box inside this water, if this box float on top of that water, just know that the relative density of that box, okay, is less than 1. Okay, the relative density of that box is less than 1. Whenever an object is floating, okay, on water, you know that the relative density of that is less than 1. Now, if the object is sinking on top of the water, I know that relative density of that substance is greater than 1. If the object just remains suspended in between the water, maybe around this place, then you know that the relative density of that substance is exactly 1. So relative density allows us to know if an object can float or can sink or be suspended in the liquid. Okay. Now that's what we call equilibrium of bodies in fluid. When we say equilibrium of body, we mean that that body or that object will remain in its position. When every force acts on that object, it will remain in its position. Then we can say that that object was at equilibrium. So in other words, an object is said to be at equilibrium when the total forces or the net forces acting on it is 0. Okay, that's when an object is in equilibrium. So the same thing when you have object in a liquid. Okay, when you put an object in a liquid, for example, now maybe this another. Let me give you a diagram again. So maybe you have the diagram here, right, and you have liquid inside this container. Now you have an object inside this liquid. Now there are two major forces that act on an object in a liquid, and number one is called the upthrust force, which we sometimes call buoyant force. Second one is called the weight. Okay. Now the upthrust force is the one that act upward. That's why it's called upthrust. Okay. It act upward while the weight is acting downward. So these two forces are the forces that act on an object. So when its body is in equilibrium, it means that the total force, let's call the upthrust force U, okay, and the weight force W. It means that W minus U is equal to 0. The reason why this minus is there is because they are acting opposite. So their net force must amount to 0. So the point where W plus minus U equal to 0, that is when the body is at equilibrium. Okay, and there is a principle that states that is behind that is, and that principle is called Archimedes principle. He said a body immersed in a fluid experiences an upthrust that is equal to the weight of the fluid displaced. That is Archimedes principle. That principle is stating that if you have a container like this, all right, and you have a liquid there, I'm doing it the second time now. If you should put an object, let's say a solid object, inside this liquid, what you will observe is that the level of the liquid will go up like this. It will go up. We call that level of liquid, that going up, we call it displaced liquid. So this is displaced liquid. Displaced liquid. Now we are trying to explain the Archimedes principle. Remember that before this object was put inside this water, there was no any increment of the level. But when the object gets in, there's a little increment. That is the displaced liquid. So he said a body immersed in a fluid experiences an upthrust. That upthrust is the upward force, like I mentioned here, is the upward force that is acting on this object. That upthrust is what made this liquid to be displaced. And he said experience an upward force which is equal to the weight of the fluid displaced. Okay. Now this upthrust that pushes this liquid up is equal to the upthrust, which is U, is equal to the weight of the liquid that is displaced. Okay, it's equal to the weight of displaced liquid. And it is true. From here, we know that from what we said before, that the net force must be zero for an object to be at equilibrium. Now, if you take u to the last side, it become weight equals to u. Okay. Now the u is the obtuse, while the weight is the weight of the displaced liquid. It was propounded by Archimedes, and it was named after him, Archimedes principle. So a body we a body that is immersed in a liquid will experience an upthrust, and this upthrust is usually equal to the weight of the liquid displaced. So this is Archimedes principle, and we can also refer to it as the law of flotation. Okay, the law of flotation. And the law of flotation is that it states that when the weight of displaced fluid equal to the weight of the body, then the object can float. So at what point will an object float? Okay, Archimedes have let us understand this concept here. Remember again, we made the container here again. This is the liquid in the container, and this is the object. Now, at what point will this object float on the liquid? The law of flotation says that this object can only float inside this liquid when the weight of the displaced liquid, you know, there will be a displacement of the liquid now as we have put it here. So now this displaced liquid here, when the weight of the displaced liquid equals the weight of this body itself, okay, that is when this body will be floating. Whenever the weight of the displaced liquid is equal to the weight of the body that's inside the liquid, then the object will float. So a body can only float when the weight of the displayed fluid equals the weight of the body. But the body will not float if the weight of the displayed liquid is lesser. Okay, if it is lesser, then it cannot float. So that is the law. And what are the applications? Okay, we use hydrometer to measure density. Okay, so we use hydrometer to measure density of a substance, and it is done using the law of flotation as well. Balloons can also float because of the average density of the balloon is lesser than air. So an object can only float when the density of that object is lesser than the density of where it is found. If the balloon density is higher, there is no way to be floating in the air. And we could also see boat and ship moving on water because the displaced liquid, the weight of the displaced liquid is equal to the weight of the boat. That is why the boat can float. If the weight of the displaced liquid are not equal, there is no way they will be able to float. Then submarines too make use of this flotation law as well. The displaced liquid, when you put the object inside the water, its weight is always equal to the weight of that object itself. So these are the area of application of the law of flotation, which is also supported by Archimedes' principle. All right. Now let us see one or two questions on all of these concepts that we have talked about. Okay. Now question 1 here says the density of a solid is defined as the A, mass of the solid compared to the mass of an equal volume of water. That's not true. This is defining relative density. It's the relative density that gave us the definition. B, amount of water displaced when the unit mass of the solid is immersed in it. No. Weight per unit volume of the solid. No. The volume per unit mass of the solid. No. Mass per unit volume of the solid. Yes. So E is the correct option. The formula for density is mass per unit volume. That's mass over volume. Okay, that's a very straightforward question. Let's see another one. Yeah, it said a body suspended by a piece of string is completely immersed in water On attempting to lift the solid out of the water, the string breaks when the solid is partly out of the water. This is because, now let us have a picture of what that statement is saying. A solid suspended by a piece of string. Okay, so let's say this is a solid. Okay, it is suspended by a piece of string. This is the string on the solid. Okay, on that, okay, a solid suspended by a piece of string. This is it here. This is the string, this line. The rope is what we call the string. It's completely immersed in water. So let's say this is the container of the water, and this is the water. Completely immersed means that that solid is totally inside the water. So let's use this line to represent water. So this is our water. Okay, this is our string, and this is our solid. Okay, our solid. So on attempting to lift the solid out of the water using the string, right? Want to take the string out of the water, want to take the solid out of the water using the string. That the string breaks when the solid is partly out of the water. So what it means is that when the solid is half away from the water, the string itself break or cut. So what really caused that? That's what they are saying. So this is because the tension in the string decreases as the solid is lifted. Now, that is not true. As you are bringing out the solid out of the string, the tension in the string should be increased. That means the force that the rope will experience should increase, because when you are taking out an object out of water, the weight of the object will definitely increase. That's what happened. Now, so that's not true. Option A is not true. Option B says the mass of the solid has increased. No, mass is a constant, so mass can never increase. It is the weight that increase due to specific gravity. So mass is a constant, so that is not true as well. See, the solid apparently weighs less when completely immersed in water than when partially immersed. Okay, that's true. Whenever you completely immerse something in water, it loses some weight. Okay, loses some weight, and that weight that it loses is referred to as the upthrust itself. So that's true. So C is true. Let's see, the say part of the solid stay in water is exerting more force on the string. No, that's not true. Once the body is out of the water, once part of the body is out of the water, there is nothing that is exerting more force on the string. Okay, the force is coming from the body that is outside the water, because once the body gets into the water, it doesn't have, no force is acting on it again. Once the body enters the water, it loses some forces, some weight actually, so it will be lesser in weight. So D is not correct. That he said the solid is no longer in equilibrium with water. No, that's not true. The correct option is option C. Option C. All right. Now let's see this one. It said the density of 400 centimeter cube of palm oil was 0.9 gram centimeter cube before frying. If the density of the oil was 0.6 gram per meter cube after frying, assume no loss of oil due to spinning. Its new volume was what? Okay, so this is very straightforward question. So the density of a substance is 400. So let's say D1 is equal to 400 centimeter cube. That's the density, okay, density of the oil, of the palm oil now. The density of the palm oil was the density of 400. This is volume. Sorry. Let's pay attention to the question again. So yeah, the density of 400 centimeter cube. So that V, volume of the oil, is 400 centimeter cube, was this. So the density of the oil is 0.9 gram per centimeter cube. Okay, before frying. So this is V1 D1. Now if the density of the oil was 0.6 gram per meter cube, now D2 now, if D2 happen to be 0.6 gram per meter cube per meter cube. After frying, assume no loss of oil due to spilling. With new volume, you have to look for V2. You have to look for V2. Okay, you have to look for V2. Remember that density formula is mass over volume. So we are assuming that the mass remains the same. That means it's going to be D1 V1 is equal to D2 V2. So we have to look for V2. So V2 as subject of the formula there will be equal to D1 times V1 over D2, right? Then from there, making our value, our D1, remember that D1 is in gram per centimeter cube, and then D2 is given to be gram per, this is a mistake, should be per centimeter cube as well. So it should be per centimeter cube. So D1 there, but in case it is not a mistake, please convert it to centimeter cube before you use. So D1 here is 0.9 times V1 400 over D2, which is 0.6. So let's now point our calculator to get our V2. So let's quickly get that. Okay, now from here we have 0.9 multiplied by 400, okay, and divided by 0.6, that is 600. So our V2 is 600, okay. So our answer here is 600 centimeter cube, okay, 600 centimeter cube. That's the correct answer, and that is option B. All right, that's option B. Okay, so we'll be doing the cutting here. I hope you have learned something today in this topic. Thank you for listening and have a wonderful day. Bye for now.